Good morning, everybody. We're going to give Zoom another 30 or 45 seconds here to let all the attendees in, and then we're going to get started. Okay, we're going to get started. Welcome everyone to the first keynote, and welcome to day 3, and welcome to day 3 of the 2021 CubeSat Developers Workshop. We've had a great couple days so far, and we're looking forward to a wonderful Thursday to close it out. We're excited to be joined by our first keynote speaker of the day, Mr. Joseph Trujillo. Mr. Trujillo is the Space Cyber Resiliency Lead for Research and Development into Technologies, Methodologies, and Processes for securing and improving the resilience of single and network space vehicles to cyber attack. He has worked in electronic attack threat warning and response for satellite systems. Mr. Trujillo also has a BS in aerospace engineering with over 25 years software architecture and development experience working in both private and DoD industries. Please, you have the floor now, Mr. Trujillo.
Right. Well, good morning, everyone, and thank you for joining me on this keynote. I work for the Air Force Research Labs at Kirtland Air Force Base in Albuquerque, New Mexico. I'm also a member of the Space ISAC. And today I'm going to briefly talk about or present what the Space ISAC is, or the Space Information Sharing and Analysis Center. And then I'm going to talk about the future space architecture, aka the small sats, and then how that is affected. What are the issues concerning cyber in this new space architecture? So the mission of Space ISAC is to facilitate collaboration across the global space industry to enhance our ability to prepare for and respond to threats, vulnerabilities, and incidents, to disseminate timely and actionable information among member entities, and to serve as a primary communications channel for the sector with respect to this information. So essentially, we want to be the one-stop shop where members can go to and be able to access information that they're interested in with respect to threats, issues with our space systems, as well as contribute to this. And at the end of this presentation, I will have a slide that shows the point of contacts and our website location. Okay, so though the Space ISAC is a new community that has just been stood up, it draws from multi-decades of collaboration between commercial, international, and government entities. There are other ISACs that exist for other domains that this is structured after. So members come from the Defense Department, intelligence community, civil and commercial or private sectors, and are involved in the small satellite community. They are leaders and vested in securing access and operation in space. Members bring with them years of experience and unique skill sets that are shared within the community, and we'd like to add yours as well. Sharing information on threats, attack surfaces, and vulnerabilities, providing educational opportunities on topics such as how the ground and space segment work, building cyber secure software best practices, just to name a few of the education items we have. We're not a political organization. We are concerned and are at the ground level and in solving real world problems. Our physical location is going to be in Colorado Springs in Colorado. That's where our headquarters will be, but we also have the online presence, which I will show you at the end. So security for space protects humanity and raises the posture of the entire sector. We're not just looking to protect space for just our nation, but healthy space domain is good for globally, right? For economy and just all the things that we do as humans, and especially since a lot of capability is being moved up into the space layer or space domain. So this slide shows the collaboration structure between the parts of the space communities. On the left, launch all the way to cloud and data processing, and government agencies such as NASA, Space Force, Space Missile Command. With the center being the one-stop location for contributing and accessing information. Essentially a repository containing information, as I talked about with the threats, but as well incidents. One of the cool things is, as a member, when SolarWinds came out, that information was available, and we get alerts in our email that tells us certain things have certain maybe hacks or systems that you're interested in have been have had some type of intrusion, and so it's a good system to be able to get at that information. As well, we have connections to our international partners such as the European Space Agency and the Japanese Space Agency, or JAXA. So all of these communities contribute, and they also receive information from this database. And we like to build this community of those members that are interested in securing space. So before I get into the future space architecture, I'd like to talk about the space system. I think a lot of people think of it as just the satellite, but it's actually, especially now, these multiple satellites, right? These constellations. There's a space-to-space interaction. There's ground to space, and then space to ground, and then there's the networks on the ground. So we have the antenna tracking stations that track the satellites. We have stations that send information to the satellites, like command and control, receive telemetry from the satellites, as well as mission data. That information or that process and that command comes from the command and control centers. As well, data is processed in processing centers, and all of this data flows through large networks on the ground and into space. So space is critical to our U.S. economy and national security. Organizations like the Department of Defense, intelligence communities, civil and commercial, all have functions that they already do in space. For example, you have the intelligence, surveillance, and reconnaissance. Think of that as having optics over where you can take a picture of any part of the world for battle assessment, for coordinating troop movements. Also position navigation and timing, PNT, think of that as the GPS constellations or constellation. As well, that we use that for our maps. And the T is kind of, the T and PNT is one of those that's kind of neglected, but it's the timing. I don't think people understand how important that is. On a global scale, when you're trying to coordinate troop movements, for example, you're going to have good timing as well. Banks use it as well, right? And nuclear detection, satellite communication, space domain awareness. As well, you have communications at the ground, the air layers. You have aviation management. Think of FAA managing the air traffic in our skies, Earth and space weather, and search and rescue. Think of Coast Guard and being able to actually find and people out in mountainous areas or in the oceans. And then you have banking and commerce. Think of bank apps, ATMs. Again, the coordination of timing of transactions is very important in this global economy. We have package tracking, and we're moving into this era of self-driving vehicles. And then last, we have the space exploration. Think of that as mining. We're moving beyond geo and towards the moon and beyond, and we're going to have exploration that is going to require other forms of PNT, as well as autonomy, being that there is a delay between Earth and our vehicles out there. So we're going to have these autonomy layers that allow the satellite to think and do things on its own. So a little bit of history here. Space has traditionally been the domain of governments and defense departments, characterized as being large satellites, expensive one-offs, usually at the MEO and GEO orbit regimes. None of these were designed with cybersecurity in mind. And you know, this is, but you know, things are changing, right? We're moving away from these types of architectures, but we still need to start, we need to think about protecting these as well. So that brings me to this next slide, which is the future of our space vehicles or architecture. So the proliferation of small form factor space vehicle constellations, characterized as being less expensive, on the order of thousands, and usually in low Earth orbit. Companies like SpaceX, OneWeb, Boeing, and others are going to be putting tens of thousands of satellites, congesting that orbit regime, but not just physically, but in the RF spectrum, right? There's going to be large networks, information going through those networks, and so we have to start thinking about how this is all going to work together as far as securing them. Small satellites, though not as capable as the larger satellites, you know, I think that the goal here is to be able to take a task and break it up among the multiple satellites to perform their small tasks to culminate to the result of a larger task, right? So what does this mean for space cyber? Well, to me, it means increased attack surfaces. Why? Because everything is moving towards being software defined. You know, software allows us to reconfigure, to update, to do changes, to add logic, especially works good for autonomy, right? But there is a double-edged sword here. That is, software is the primary attack surface for hackers. As well, you have everything being connected. Think of the Internet of Things of space. So on the ground, we have all of these networks and all of these devices like sensors, cameras, temperature gauges. All of this is now going to move up into space, and now we're going to basically extend the network to be able to add more attack surface, not just to space, but then everything that it's connected to. And then you have the autonomy software layer. Because of the dynamics of LEO, the fast motion, and just the complexity of the operations that need to occur, we're going to have autonomy software layers, which we have to be able to trust the autonomy. So we have to start thinking about protecting these layers. And then you have edge processing and learning. We're pushing the processing up into space to give it more capability. But we have to also understand that that puts a lot of risk on our space assets, and so we have to protect there as well. And then you have the hybrid constellations. In this case, you know, like SpaceX and Boeing, and others that are going to be able to, you know, use our sensors to gather information or data, process it, share it, or move data across other constellations. For example, SpaceX could pass data through the Boeing if there's a contract set up between them that allows them to pass information quicker. So we have to start thinking about how to protect our data from these different types of networks that it's going to flow through. So ground-based space support systems, I talked a little bit about this, but you know, you have the antennas that track, that transmit and receive. You have the stations that control them. You have the command and control centers that issue the commands. All of these run on a network or networks within networks. Some of them push information up to the cloud or have to go through the internet backbone and tunnel through it to push information to other networks. Obviously, that adds a lot to the attack surface as well. All of these run on software, for example, like data analytics, data distribution, data fusion. There are many applications and tools that operators use that are able to control the systems. And then a good example is the antenna with respect to firmware. So somebody may write logic and software to control an antenna to track a satellite, but that actually talks to firmware to a machine that has machine code that essentially controls the motor that turns the antenna. So you can see that there is just a large chain of attack surfaces within this whole concept right on the ground. So here I have the space vehicle, and here you have the functions starting at the TT&C radio, the hardware, GPS, power control, propulsion. All of those have the firmware that help them operate. As well, they place data on a network bus. On the other side, you have a payload hanging off the network bus that may have sensors hanging off it that have their own software and their own firmware. So this is a mini network within the satellite that needs to be protected. As well, on the lower right there, you have in green the flight software. So that runs on a flight computer runs on top of the real-time operating system and any platform-specific software layers. And then you get the more higher level functions like the command and data handling, the attitude control system, power, thermal, and PNT. So all of these are software, firmware, networks, again, within the satellite attack surfaces, right? So moving to the future layers, aka the small sats, the PLEO, now you're going to have multiple satellites all connected. And the main change here is the crosslinks on the payload, right? The components are antennas, software-defined radios, the digital signal processing software or firmware, and just that's another attack surface that we need to consider. And as well, we've added new layers of software like reconfigurability and updatability. That capability is there. Multi-agent behavior software, autonomy, and distributed processing. So in conclusion, and I think this is perfect for this group here, being that people are interested in small sats. The first bullet point, design and cybersecurity, is very important. The large players, it takes them some time to change and move, right? But with small sats, you can play and you can onboard new capabilities and see how they're going to play out. And so I want everybody to start thinking about designing in that cybersecurity from the get-go, right? To kind of throw away what's already out there. Take the lessons learned, of course, but maybe the architecture of software looks different when you're trying to protect it versus what they've done in the past, which is make it more functional or swap capable, right? Because they're always concerned about power on these things. And so we need to start thinking about different ways to do this. For monitoring detection, those are good concepts. We need to be able to detect when we've been attacked and also learn about the attack, right? So we can get better. But I put there a paradigm shift because we don't want to add to the attack surface by adding these components. So again, how do we bake this into the system so that we don't just keep opening up more attack surface? And then isolation, recovery, and self-healing. So all of this depends upon having modular software, which I think most of you are moving to, but there's still some issues with people having monolithic types of software. We need modular software simply because we can isolate. So if there's a compromise in one module, we can isolate that and go about recovery and then self-healing. And then they have cyber situational awareness. So this is about building tools and applications that human operators can use to get the situational awareness of cyber, right? Not only in space, but on the ground. I mean, a lot of this happens without anybody knowing. It happens at the bit level, at the data level, at the network level. We need to roll this up into what humans can understand so that they can understand not only locally what's going on, but globally what's going on. Then you have the cyber artificial intelligence and human interaction. So as I said, we're going to need artificial intelligence, and we're moving towards that so that we can operate in these more dynamic environments. Cyber is a speed of light attack, but we also want to build this up gradually where we have that human interaction so we don't miss steps. And so that doesn't mean that we won't end up at a full AI at some point, but we need to build up so that we can build a good base that our AI sits on. And then last, you have the learning on the edge for continuous evolution and protection. So once we're able to detect an attack and isolate it and recover, the one word I think of here is zero-day attack, right? We think we've fixed all the bugs, we think we know all the signatures or categories of viruses out there, and then we always lose that game, right? You know, there's always new hacks that come out. So we need to get better, obviously, at detection and recovery, but we also need to have some type of onboard learning and evolution of our software that is based upon and forced by these the changing cyber environment. So this last slide here shows the point of contacts and the information for the Space ISAC organization. Aaron Miller is the executive director. Carrie Hardy is membership and marketing manager. And at the bottom left there is our website. I think, I did a brief explanation of the Space ISAC, but I think I didn't do it enough justice. So going to that website, you can get a lot more details on what we're about and what information and what capabilities we provide, and maybe you see yourself as a good contributor to this. And I think that the small sat community definitely can play in this field and help push our needs for cyber. So thank you all for coming, and have a good rest of the day.
Yes, and thank you, Mr. Trujillo, for the presentation. I enjoyed it. We now have a short break while we get ready for the next session, so you can stretch your legs, and we hope to see you at 9:30.